Ladies and gentlemen, this is a multiple choice question from the AP Physics exam, not from this year, obviously. And go ahead and pause the video and do your best to answer it.
Well, show them what kind of graph we've got here.
So, when I first looked at this graph, I was like, there's nothing on the graph. And when you look at the graph, we see that it's a force by
Versus time.
What's the word I'm looking for? Force versus time graph, and we have these dots right here, right? And it wants to know, it says the increase in the momentum of the object between t equals 0, at this point here, and 4 seconds, is most nearly which of the following?
So pause this, put your head to it, see what y'all can do.
Before you give up, say, Miss Moore, I can't do it. Look at it. What do you see? Well, I can't count. 1, 2, 4. 3. What do you know about momentum?
And what does it take to change momentum? If momentum is increasing, what's causing it to increase that would be, and how can we get that information out of a graph?
I probably didn't need to do all this,
No.
but I'm doing it. It goes up to right
25,
there.
just about, I'm going to call that 25 because
Okay.
it's most nearly.
So it looks like something like this, right? And we know that impulse equals force times delta t.
Yep.
Well, lucky for us, we have force, and we have time. So basically, this times this can give us our answer, yes?
Yep.
Okay, so it's going to be, okay, well, hold on. We have a couple of different shapes here, right?
Yes, we do.
So
In 4
we
seconds.
have this shape,
Yep.
and we have this shape. Yay, shapes. Okay, so let's go ahead and do our force, which is 5 times 4. 5 times 4 is...
That's right, because the area underneath the line is equal to the impulse.
That's what I needed to tell them. So 20 Newton seconds. And then this one is going to be half of 4 times 15? 4 times, is that right?
Let's see, 25 minus 5 is what?
25 minus 5 is 20.
Yep.
Oh yeah, it goes all the way up to 25, right?
Yep.
Yeah. So is 20 times
20 newtons.
times 4. That's going to be 50, right? That's 80 divided by 2 is
40.
40. Okay. Newton
So the
seconds.
total area is going to be,
Did you guys get letter C?
it's
I did.
letter C.
Letter C. Okay. A system, and we've seen the word system before. A defined set of objects, the energy and momentum associated with them.
Okay.
Internal forces exerted by the objects on each other.
Those are forces inside the system.
Newton's third law says these sum to 0.
Equal in magnitude, opposite in direction.
My mouse is freezing. External forces come from outside of the system. In an isolated system, external forces sum to 0.
Nothing coming in, nothing going out.
Okay. All right, conservation of linear momentum. The total momentum of a closed isolated system is constant. The momentum total before equals the total momentum after. And we saw this with energy.
Yep.
Same concept.
Conservation laws, gotta love them.
Yeah. Okay. There are two general categories of conservation of momentum examples. We have explosions and collisions. Today, we are only going to focus on explosions.
What is an explosion?
I don't know. Okay. Let's go ahead and give an example of an explosion.
Well, first,
Oh, we want to talk about this one?
Yeah.
Sorry. Okay. So, what does our law of conservation of momentum really mean right here?
Yeah.
Well, essentially, we have the momentum at the very beginning.
Yeah.
of whatever we're doing. The event takes
Something
place.
happens. Could be a collision. Could be an explosion.
Collision or explosion. And today we're focusing on explosions, but it could be collision. And then we have the momentum after.
Yep.
Okay, and they are equal to each other. Okay, so is my next slide the one? Yeah. Wait, do I want to go to this one or want to go?
You do.
Okay, we'll leave it here. So explosion.
That's where the total momentum is 0.
Okay, let's have an explosion.
Uh-oh.
Okay.
Got a skateboard.
Miss Moore does not ride a skateboard. You can tell by the way she gets on the skateboard. Both my sisters ride a skateboard. I do not. Okay, the first question for you guys is, what is my momentum right now?
Well, you're not moving. You got mass, but you're not moving. It's 0.
Exactly. Okay, so I'm going to go ahead and squat down here, and I'm going to go ahead and create my explosion.
Whoa, the ball went that way, and you went that way.
Now what am I? What's my momentum now?
Well, right after the explosion.
I don't like doing an air squat right there. Okay. So, let's draw a picture. What was my momentum before? What was my momentum after for our explosion? All right, so let's go ahead and draw a diagram to really understand what's happening here. So we have Miss Mo. Let's define our system here. Okay. We have Miss Mo. We have the ball. And we have the board.
Yep.
Right? And we know that the momentum total is going to be 0.
You were just sitting there.
Yeah.
And
it's an
before the explosion happened.
Just chilling, okay. And what happened was the ball went this way.
It did.
Okay, so that's the
Crashed into that styrofoam thing over there.
the momentum after that way, yeah. And then I went
The other way.
the other way, right? Woohoo! Okay, and I went this way. The momentum of Miss Mo, and this is the momentum of the ball.
So the law of conservation momentum says momentum before is equal to momentum afterwards. How can the momentum afterwards be 0 if you be moving and the ball be moving?
Okay, so what Boykin is saying is that this plus this is going to equal 0. How can that be?
Well, that's pretty simple.
Well, one of these has to be a negative,
That's right.
and this one must be a positive
Yep.
to get me 0, okay? So should we throw some numbers in here real quick?
Well, I think you put the letters in.
Oh, yeah, okay.
Because the ball
yeah.
has a small mass and a large velocity.
So over here, we have a small mass and a big velocity. Over here, big mass for Miss Mo, and small velocity. And because the explosion equals 0. Now, what I forgot to do is I'm subtracting this to get it over here. So I have M big V equals negative M little v. I'm subtracting this right now. It's being added. I'm subtracting it over here. So now as we follow this through though, we know that this needs to be a negative number and this needs to be a positive number. Okay, so then we plugged some numbers in. We said, what was it, 7 kilograms times negative 5 meters per second equals, and my mass was negative 65 kilograms, I think I said, times velocity. We want to figure out what the velocity is. So basically, negative 35, I'm running out of room. I'm going to say negative 35 kilogram meters per second divided by, I'm just going to divide by negative 65 kilograms is going to equal my velocity. And when I do this, 35 divided by 65, that's when I get my 0.54 meters per second. And let's take a look at our signs to make sure everything is making sense here. We know that this side over here should have been a negative number. Okay, this was a negative number right here, sweet. And we know that over here, ultimately, our answer should have been positive. Okay, we have a positive velocity here. I hope that makes sense. Ultimately, what you need to understand is that in order for my explosion which equals 0, to work out, you have to have these two have to cancel each other out. And we see that here. We have our mass times our velocity. We have our mass times our velocity. We divide by our mass to get our velocity by itself, and that is the velocity that Miss Moore was moving that way. Okay, so here are your homework problems in the regular physics book. Regular physics problems in the regular physics book. Page 214, numbers 13, 14, 15, and 16.
You know what I'm thinking? Let's just put some numbers in to give them Let's say that bowling ball has a mass of 7 kilograms.
70?
7. Oh,
just sorry. You know what?
No.
I just realized that negative, like that. Okay, 70?
Not 77.
Oh, sorry.
You can put 7.0. 7 kilograms.
7 kilograms.
And let's say the velocity is 5 meters per second.
Negative 5 meters per second. Okay.
And the mass of you is what,
I
65?
think I'm 65.
And we want to find out how fast you were going. How can
Yeah.
we solve for how fast Ms. Mo was going?
Okay, well, can I just move this over here?
Yeah.
Divide by 65, divide by 65 kilograms. Okay, and my velocity is going to equal, so 7 times a negative 5 is negative 35. And I divide by 64, and I get negative 0.5.
Okay, so 0.5 meters per second. And what you've got is this negative right here has to go down here. Because you're going in the positive direction, right?
Oh, so we're saying,
Keep this here,
gotcha. We
put a
want to
negative
keep
right-
it there. Oh, that's a great point, Boykin. Okay, so so we know that the velocity is negative, so we put the velocity negative
Because
there.
you were going in that direction. You were going in the make that thing positive over there.
Oh, boom.
It's going to feel bad about it.
Okay. That is
Alright.
a really good point. I see it. And that's why it's so important that you take a step back and think about this has to be negative, that has to be positive to get you this answer. So we have to keep that negative sign right here and bring it down there.
Now, I bet they can knock these things out like nothing.
Easy, easy. Go ahead and begin.